All right, everyone, good afternoon. So happy Friday to one and all. Before we go to the weekend, we have lecture. And then if you want to join this week, we have a lab. I would recommend you do the lab and have next week to do the lab report. But you can do either or. And so let us start things off with some housekeeping work. Today's February 26th, 2021. If you have not already, please turn in your homework 13. I gave 10 points to those that turned it in this morning. So homework 13 is due. Another thing here is start working on homework 14. I made the due date, and it's flexible, but I made the due date next Friday. Okay. I believe that is the March 5th. So whatever it is, turn that in and I'll give you the 10 points. Start working on quiz 2. Okay, the due date for that is actually March 8th, which means your next exam is going to be March 8th. And it will be the same format as test number 1. Okay, that will be a Monday, and it's the same format, multiple choice and a problem set. So be aware of that. We'll have a review the Friday before. This is a Monday, by the way. And another thing, for those of you that have paid the $30, do your clutch prep drills, and I'll give you some extra credit at the end of the term, provided you do everything. Okay? You have to do everything, all the problems they give you and all the videos they give you. And this should help you reinforce the material. And then labs, there's a lab report. We're starting a new lab, so the lab report on freezing point depression is due. So make sure you turn that in. Make sure you turn it in today or this weekend. All right, I believe only one person has turned it in. So please turn that in, and I'll look at it and give the points. And finally, this is what I have on my list. A new lab today, and that's kinetic. The lab is rates of reaction. Okay, so lab today, rates of reaction. All right, so it's an interesting lab. I think you'll like it. It's a heavy lab for the post lab and all that calculations. Having said that, it's a pretty good lab. I think you'll enjoy it, so make sure after today's class, after you get your break, you come and take the lab. Bless you. It will be available next week, but I do recommend you take it and do this lab, the lab work, and reserve next week to focus on your lab report. That's my advice. This is all that I can think of. Anybody can think of anything else? Think anything else? Joshua, anybody? All right, so I think I got everything here for now. The big news is the test that's coming up in not next week, but the week after next. Not next week, but the week after next, which is March 8th. So more information will be provided to you there. If you want to get a heads up, there's a study guide up already on Canvas. And it will cover chapter 13 and 14. All right. All right, so let's move on here. We're talking about equilibrium. Okay, equilibrium, capital K. And that is known as the equilibrium constant. Okay, which way will the reaction proceed? Okay, the reaction is not going 100%. So it will settle. Will it settle more products than reactants? More reactants than products? Okay, which way will the reaction settle? Okay. It will move in such a way such that it will settle in a certain concentration of products or reactants. If it's 50-50, the equilibrium constant is 1. Okay. So which way will it settle? You'll have some reactants and some products left over at the end. Now I want to tell you, if this is the equilibrium, if you disturb it, it's going to go back to the original state. Okay. So if you disturb an equilibrium, it will go back to reestablish equilibrium. Right. That is like if you push me, I'm going to fall back, but then I'm going to come back to my original place to continue lecture. Okay. So if you disturb an equilibrium, it will come back to the original equilibrium concentrations. Equilibrium concentrations of products and equilibrium concentrations of reactants. All right. Here's some rules here with regarding K. Okay. So I like to call this gymnastics. K gymnastics. So what does gymnastics mean to you? Maybe flipping, twirling, okay? That's gymnastics. So what does that imply when we talk about K, equilibrium constant K, law of mass action? Right? So let's say we have two reactions, okay, reaction 1 and reaction 2. If you add two reactions, okay, you'll get a new reaction. What's the new K value? The new K value is the multiplication of K1 and K2. So when you add two reaction, you multiply the Ks to get the new K. Multiply the equilibrium constant to get the new equilibrium constant. To get the new K, right? So what you see here is equation 1 and equation 2. What I've done is I've added 1 and 2 together here in the red box. So what is the new K? For this, the equilibrium constant for this reaction, it's going to be K, this, I'll call it C1, times KC2. You have to multiply the equilibrium constants. Right. So I also find this to be a weak point based on my previous experience. Adding two reactions, multiply the equilibrium constants. Once again, when you add two reactions, you multiply the equilibrium constant. So that's rule number 1. I'll call that I. Let's do rule number 2, Roman numeral 2. When you multiply a reaction by a number, you take the power. You raise the equilibrium constant to the power. All right. So in other words, here, look at this reaction with me. All right. I'm going to multiply it by 2. Just take a 2 and multiply it all the way out. And when I multiply it by 2, I get this. So this reaction here is multiplied by 2. So what is the new equilibrium constant? Well, I multiplied this whole reaction by 2. The new equilibrium constant is K raised to the power of 2, because I multiplied the whole reaction by 2. The new equilibrium constant gets raised to the power of 2. Okay, does everyone see that? Once again, multiply this reaction by 2, so 2 times 1/2 is just 1, goes to 2 NO2. This is the original equilibrium constant. my new equilibrium constant is now that one squared. That one squared. What happens if I multiply this by 3? What will my new equilibrium constant be? It will be k cubed. What happens if I multiply this reaction by 4? I'll do that in green. If I multiply this reaction by 4, okay, 4 times 1/2 is 2, goes back and forth to 2NO2. If I multiply the reaction by 4, the equilibrium constant gets raised to the power 4 for this new reaction. Okay, so everyone see that? The power, if you multiply a reaction by some number. All right, let's talk about rule number 3 now. Rule number 3 is when you flip a reaction. Okay, when you flip a reaction. What does flipping mean? Okay, gymnastics. When you flip a reaction, what will you do? You will take the reciprocal to get the new equilibrium constant. Reciprocal. Flipping, you see, means the products now become the reactants, and the reactants now become the products. And that's what we did over here in this reaction. So in this black box, black ink box, we flipped this reaction by the dot. We flipped it. And what's our new equilibrium constant? Okay, it's going to be the reciprocal. So the new equilibrium constant is 1 over that. Okay, we flip it, so you take the reciprocal. Mu k, which is equilibrium constant, is the reciprocal after you flip the reaction. So flip a reaction. What do you do for the new equilibrium constant? Take the reciprocal. Okay, multiply a reaction by 3, new equilibrium constant, raise it to the 3rd power, add 2 reactions, multiply the equilibrium constants together. Add 3 reactions, multiply K1 times K2 times K3. All right. So once again, K is our equilibrium constant. It's products over reactants. Okay, raised to the stoichiometric coefficient. Products over reactants raised to the coefficient. Okay, so I'll call that SC. SC stands for stoichiometric coefficient. And the big thing here, the big rule, is no solids, no liquids. That is our equilibrium constant. We see this all the time where students accidentally put solids and liquids in there by accident because, you know, it's easy to do that, okay, if you're not careful. Remember, okay, we have to be very keen now because we're in the higher level chemistries. These are all equilibriums. Okay, how do I know they're equilibriums? Like driving the car, you got 10 different things going on at the same time. Solving a chemistry problem, you got to look at 10 different things, and one of the things you got to look at is the reaction arrow. Okay, the reaction arrow going back and forth tells us this is an equilibrium. It will have an equilibrium constant. Okay, the magnitude of this equilibrium constant tells us. Okay, where's our little scale here? It tells us, will we have more products than reactants, or more reactants than products? If it's 50-50, it's 1. All right, so this concludes the topic of gymnastics. What do you do when you manipulate reactions? What happens to the new equilibrium constant? All right, now I want to teach you guys something a little bit new here, and that is called the Gator Rule. All right, the Gator Rule. Before I teach you guys the Gator Rule, I have to introduce something called the reaction quotient Q. Okay. The reaction quotient Q. So if you look here, instead of me writing it out, here's the equation for Q, reaction quotient. And by the way, okay, this is strange. Here's the equation for K that we learned, law of mass action. Okay, so what's the difference between Q and K? Is there a difference in this reaction? Is there a difference between Q and K? The answer is no. Okay, the equation is the same. What's the difference? This is the most important thing. These concentrations for K are equilibrium concentrations. The concentrations are at equilibrium. Okay, that's K. Q, same equation. Everything is the same. Q is exactly the same equation, but they may or may not be equilibrium concentrations. They may or may not be. Okay, how do we know if they're equilibrium or not? Okay, we have to compare Q to K. Okay, so let me write this down for you guys. What is Q? Let's move all the way up here. So these are equilibrium concentrations for K, but Q is the same as K. So let's write this down here. Q, reaction quotient Q is the same as K. Same equation as K, equilibrium constant. But we ask ourselves the question, are these equilibrium concentrations? We ask ourselves the question, are these equilibrium concentrations? We ask ourselves the question, are these equilibrium concentrations? If they are not, equilibrium concentrations, which way will the reaction shift to achieve equilibrium? Which way will the reaction shift to establish equilibrium? Which way will the reaction shift? So that is where Q comes into the picture. Okay. So I want you to recognize and realize that Q basically is just used to compare to K. We use Q and compare it to K. It's the same equation. The only difference is K is the established equilibrium concentrations, the established equilibrium constant at a specific temperature. Q, we don't know. We don't know. Okay? So we always compare Q to K. Now I'd like to always compare, just write that here, compare Q to K, or compare Q with K. Compare Q to K. Right. So now let me talk to you guys about the Gator rule. So Q is equal to K, same equation, but it's just used for comparison. For comparison. All right, now let's talk about the Gator rule, and this will make sense when we do some practice problems here. Okay. All right, the first very, very extremely important rule is that you have to put Q first. Remember, we compare Q with K, but to do the Gator rule, otherwise this rule will not work, put Q first, okay? So we compare Q with K. Okay, we want to put Q first. Okay, this is very important, otherwise what I'm teaching you is just wrong. Okay, unless you put Q first, then what I'm teaching you here, this little trick, is correct. Alright, so we're going to put Q first here. We got 3 conditions. Alright, remember, see, look everyone, I'm putting Q first. Everyone look, Q goes first. Okay, the easiest one is if Q is equal to K, then what? Then we have equilibrium concentrations. Okay. So if Q is equal to K, then we are at equilibrium. Those are the equilibrium concentrations. These are equilibrium concentrations. I'll just use the bracket for concentrations, okay? If Q is equal to K, the number, remember these are unitless, if Q is equal to K, then we are at equilibrium. These are indeed equilibrium concentrations. Okay, so we have Q and K. So we have Q, what we put in here is at equilibrium. Q is, I'll put here non-equilibrium, question mark. Well, if you put your numbers in the problem, you solve the problem, you put the numbers in, and if Q equals K, you're at equilibrium. Now what happens in our first scenario if Q is greater than K? Okay, which way are the Gator jaws pointing? To the left or the right? Left, right? Yeah, the Gator jaws are pointing to the left. So which way will the reaction shift to establish equilibrium? Which way will the reaction shift to get to the equilibrium concentrations? Okay, where's the alligator jaws pointing? Left. Which way will the reaction shift? Left. Okay, that's where the Gator jaws are pointing. Okay, so the reaction will shift left to establish equilibrium towards the reactant side. That's where the Gator is pointing. So reaction shifts left to establish equilibrium. Okay, reactant side, right? That's the reactant side to establish equilibrium. I'll just call equilibrium EQ. And what happens if Q is less than K? Where are the alligator jaws pointing? Where are the gator? To the right. Okay, you see this, the jaws pointing to the right. Where will the reaction shift to establish equilibrium? To the right. Reaction shifts right to establish equilibrium. I'll just put EQ for equilibrium. Once again, remember equilibrium. Okay, it settles. And what happens if I disturb the equilibrium? If I disturb it, okay, it's going to move back to where it was before. Okay, if you push me, you see I'm comfortable here, but if you push me, I'm going to go back to where I'm comfortable at, like this. Okay, equilibrium reactions will always settle to where they were before, such that it equals the equilibrium constant at a temperature. Once again, if you push me, I'm not going to go back there. I'm not going to stay there. I'm coming back right here to lecture. Right? If you push a reaction, it's going to go back to where it's comfortable. Where is it comfortable? Equilibrium. What is equilibrium? Okay, where it equals to the equilibrium constant at that temperature. All right, so that is Q and that is K. Okay, Q and K are the same thing, but it's only used to compare. Okay, we're comparing. Remember, again, these numbers are unitless, so there's really, you're just comparing a number. Okay, you don't have to worry about units for equilibrium constant. All right, so there you see some gators, alligators, and then just look for where the jaw is pointing at. Okay, this will only work if you put Q first. Okay, this will only work if you put Q first. If you don't do this, then the answer will be wrong. It will be flipped. It'll be incorrect. Okay, it'll be incorrect because it's flipped. The only way this works if you put Q first. In fact, if you look at your textbook, they didn't put Q first. Okay. So, naughty textbook. They didn't put Q first, they put K first, so this is the opposite of what I've shown you in your previous notes. All right? But if you put Q first, you can go to if you put Q first, you can use the Gator Rule and see where are those alligator jaws pointing at. Okay. All right, let's do a problem that illustrates this. All right, so the Kc, the C here stands for concentration, for the following reaction is 6.5 times 10 to the 4 at 35 degrees. 6.5 times 10 to the 4. Okay, that's a pretty big number. Okay, so where this equilibrium resides, 6.5 times 10 to the 4, okay, more products. Okay, 6.5 times 10 to the 4. That's a big number, times 10 to the 4. What is that, 10 to the 4? 10,000, so 65,000? Yeah, that's $65,000. Okay, you're moving forward in life. Okay, here's the reaction. We quoted this at a specific temperature. In a certain experiment, 0.020 moles of NO, 0.0083 moles of Cl2, and 6.7 moles of NaCl are mixed in a 2-liter flask. In which direction will the system proceed to reach equilibrium? Okay. Let's put a question mark here. Okay, so the first thing you need to do here is compute the concentrations. Okay. So step 1 is compute concentrations. Okay, remember, concentration is moles over liter. So let's do the concentration of NO here. The concentration of NO is 0.02 moles. How many liters is this all in? 2 liters. So the concentration of NO, when we mix all three of these gases together, is 0.01 molar. All right, let's look at the concentration of Cl2. The concentration of Cl2 is 6.7 moles divided by 2 liters. And that is what, that is 3.35 big M. No, wait, Cl2. Oh, sorry. Wrote the wrong thing there. The concentration of Cl2, 0.0083. It's in a 2-liter flask, so 0.0083 moles divided by 2 liters is 0.00415 big M. And then finally, the concentration of NaCl, let's put that in pink here. The concentration of NaCl is equal to 6.7 moles divided by 2 liters, and this is 3.35 big M. So step one is we have to compute the concentration of each of these guys. I'll tell you another mistake students make. The mistake students make is they put moles in. Okay, you have to do concentrations. Okay, don't put moles. Put the concentrations into your equilibrium constant. Right, by the way, what is the equilibrium constant for this? K is equal to what divided by what? Concentration of NaCl. What should I do with that NaCl? What should I do with that NaCl? I should square it. Products over reactants divided by NO. What should I do with that NO? Square it. Concentration of Cl2. Okay, so that is equal to 6.5 times 10 to the 4th at 35 degrees. Everyone see that? Okay, law of mass action. All right, so we got step one. So now step two here is, are these really the equilibrium concentrations? Is this the equilibrium? Is this at equilibrium? And is this at equilibrium? Are these really the equilibrium concentrations? Okay, are these equilibrium concentrations? And we will test that by computing Q and comparing with K. Computing Q and comparing with K. All right, so let's do this thing here. So we have Q, remember it's the exact same equation. Okay, so NaCl squared divided by NO squared times Cl2. All right, so the concentration of NaCl is 3.35. Square that, divided by the concentration of NO squared, 0.01. times the concentration of Cl2, 0.00415. So plugging our concentrations in, I'll just go ahead and give you the answer. On my calculator, I was getting 2.70 times 10 to the 7th. Okay. 2.70 times 10 to the 7th. So are we at equilibrium? No. Okay. These are not equilibrium concentrations. Okay. Why are these not equilibrium concentrations? This is the equilibrium constant value. Under these concentrations and plugging it into the equation, we're getting this value. It's not at equilibrium. Which way will this go to get to equilibrium? Remember, if you push me and I fall all the way back here, okay, I'm not staying here. Okay, I'm coming back. Okay, which way will this reaction go to establish that equilibrium? All right, put Q first. Okay, everyone put Q first. All right, so we have Q and K. Q as 2.70 times 10 to the 7th. K, okay, they gave us K in the problem, 6.5 times 10 to the 4th. All right, who's bigger? Q is bigger, very good. Okay, so which way will this reaction shift to get to equilibrium? Towards the product side or towards the reactant side? Left, which is the reactant side. Okay, that's where the jaws are pointing, the alligator jaws. Okay, you see that? Pointing to the left. So this reaction will shift to the reactant side, as Elena said, or it will shift to the left to get to equilibrium. We're not at equilibrium, but to get to equilibrium, the reaction will shift left. Okay. So that's how you do a reaction quotient problem. All right, I made some videos of your homework problems for chapter 14, so check that out. They'll walk you through some of your homework problems to get more help and practice on this. And I'm pretty sure you'll see this on the quiz and on the exam, which is coming up not next Monday, but the following Monday. All right. So this is the Gator Rule. This is what I'm teaching you. If for whatever reason, doesn't make sense, you can use the textbook rule. Just remember, if you use the Gator Rule, which I'm teaching you, put Q first. Okay, otherwise you'll get the wrong answer. You have to put Q first. Another thing, what goes inside here? Concentrations goes. Okay, don't put 0.0083 moles here. Don't put 6.7 moles there. Don't put 0.020 moles here. Okay, it's moles over liter. Moles over liter. That's another mistake. What goes in here is moles over liter, not moles. Moles over liter goes in here. All right, now something new here. And now this is called the ICE table. Okay, so this is something that gives students a lot of heartache and issues. So let's go over this. And this is something we'll probably spend next week on. So here we go. Something that's totally new, something that may be foreign to a lot of us, and that is called ICE tables. Okay. ice tables are used to determine the final equilibrium concentrations. The final concentrations at equilibrium. ICE stands for initial, change is the C, so initial, change, and then finally E stands for equilibrium. Equilibrium. ICE tables, all right? So why don't we go in here? Let's let's dive head first into an ICE table problem. Okay. And let's do that right here. Let's see if we can finish this in the last 10 minutes or so. Okay. All right. So starting with an initial concentration of 0.040 molar HI. What is the equilibrium concentration? Let's highlight that in pink. What is the equilibrium concentration? What is the equilibrium concentration of HI, H2, and I2? Okay. So there is a piece of information that's missing here. So obviously on an exam, I can't give you this and expect you to solve it. I have to give you the equilibrium constant. Okay, so on the exam, I'll give you the equilibrium constant, and the equilibrium constant that I found is 54.3, and I found it for this reaction at 430 degrees C. You need this to solve this problem, otherwise you cannot solve this problem. All right? You need the equilibrium constant. All right, so you see the word initially. Okay, initially is not the same as finally, right? Is initially, all right? Initially, I woke up tired, okay? I'm going to go to bed 12 hours later. Okay, how about this example? Initially, I woke up hungry, okay? Well, 8 hours later, I'm going to go to bed with my tummy full, okay? Well fed with a good dinner. Well, initially, we're at 0.040 molar HI. Okay, what will we be at finally? Okay, well, remember, in an equilibrium, we have, what do we have at an equilibrium? What do we have at an equilibrium? Okay, not all products and not all reactants. Okay, we have some reactants, some products. Okay, which one is more, which one is less? That's not the point. The point is, at the end of the reaction, we're going to have HI, but what else will we also have? We will also have H2 and I2. Okay? We will also have H2 and I2, because that's what an equilibrium is. So the first step here is to set up our ICE table. Have you ever heard that Vanilla Ice song? This was in the 90s. I grew up in the 90s. Ice, ice, baby, vanilla ice. When I say this, I keep thinking of that song by that guy. No? You don't get it? You get it? Okay, thank you. We have a connection there with that Vanilla Ice song. Respect, yeah, I guess, for him, the ice, ice, baby, vanilla ice. All right, so we will set up our ICE table. ICE. All right, initially we are at, so remember, this is initial, change, and equilibrium. Initially we are at 0.040 molar HI. Big M. Initially. Also, initially we are at 0 and 0. Does everyone see that? So initially we're at this much. Obviously that's not going to be finally. Okay, some of the reaction will have to move. It's going to move this way. It has to. Okay, why? Equilibriums. Okay, we will have some reactants and some products left over when this whole thing settles. So what is the change here? All right, how many moles of how many moles of HI are there? 2. So it's going to shift this way, okay, because we have to have some I2, we have to have some H2, but it's not going to shift minus X. Okay, it's going to shift minus 2X because of the 2 there. Okay, it has to shift minus 2X. This will shift plus X. This will shift plus X. Okay, the reaction is moving this way because in an equilibrium, there's going to be some reactants along with some of the products. Right, so our equilibrium at the end of this reaction, at the end of the hour, at the end of the day, at the end of the month, at the end of the year, when it's all said and done, we will have an equilibrium concentration of X, and 0.040 minus 2X. So these are the equilibrium concentrations at the end of the reaction. These are the equilibrium concentrations at the end of the reaction. So at the last 5 minutes, let's see if we can solve this. If these are the equilibrium concentrations, let's put it into our equilibrium expression. Step 2, put into equilibrium expression. All right, so our K here is going to equal to concentration of HI squared divided by concentration of H2 times the concentration of I2. Okay, right? Products over reactants. All right, the equilibrium concentration of HI is going to be 0.040 minus 2X. So this K here is 54.3. That's given. Equals concentration of equilibrium for HI is 0.040 minus 2X squared times concentration of H2 is X. Concentration of I2 is X. Everyone see that? X and X. So X and X is X squared. All right, now what I'm going to do is I'm going to take the square root of both sides of the equation. Okay. So basically I plugged in my ice table into the equilibrium concentrations, equilibrium expression. The square root of 54.3, so I'm just going to take the square root of both sides. Okay. Square root of 54.3 is 7.37. Square root of this squared over that squared. Okay, square root of that whole thing squared. I'm going to move the square above. So it's just going to be 0.040 minus 2x divided by x. Right, square root of this is 0.04 minus 2x. Square root of x squared is x. Okay, take the squared and square over square will make it whole square. All right, let's solve for x here. We have 7.37x is equal to 0.040 minus 2x. All right, let's move the minus 2x to this side. So 2x plus 7.37x is 9.37x equals to 0.40. So x is going to equal to 0.04. So x is going to equal to 0.04 minus 9.37. And that is, on my calculator, 0.0043. Okay, here we want to put our units big M. And that is not our final answer, but we are almost there. That is our x. That is our equilibrium concentration for H2, that guy. That is our equilibrium concentration for I2, that guy. And our equilibrium concentration for HI is 0.04 minus 2 times this. So our final answer is this, our equilibrium concentration. And let's see if we can finish this off at equilibrium. We will have a concentration of H2, which is X. H2 is X, which is 0.0043. Big M, here you want to put the units. We will have a concentration of I2, which is X, 0.0043. Here you want to put the units big M. And then HI, what is HI at equilibrium? It's not X, it's 0.04 minus 2X. So 0.04 minus 2X, well, we solved for X here, 0.0043. And we are getting an answer of 0.0315 big M. And that is our answer here. Okay. So we will review this on Monday. And by the way, there's a way to check your answer. How do you check your answer? Plug this into that. Plug that into this, plug that into this, see if it equals to 54.3. So there's a way to check your answer at the end of the exam to make sure you got it right. All right, I will tell you that we will see a lot of ice tables in this course. Okay, you will see that from here on out. You'll see it in chapter 15. You'll see it in chapter 16. So now's the time to know this more than ever. Now's the time to know this because you will see this again very much. It will rear its head many, many times in the next month or so. All right, ice tables. There's one more ice table problem on Monday. And have a good weekend. If you're coming to lab, I'll see you in the lab.